2.303 or T log 10 K equilibrium. This is what you write here. Okay. What does this mean? What is R? This is a heat, this is a gas constant. This gas constant approximately equals 23,000 kJl per mole per degree. What is T? Kelvin, that's the temperature. What is the KEQ? Right here. So a little bit of mass. If this KEQ is larger than 0, what this means, I'll give you an example. If log 10, that equals 1, there is a negative at here, which means delta G prime will be less than 0. So spontaneous reaction will happen. And we have a terminology called exogonic reaction. And that is exogonic. And if this KEQ is less than 0, and I give you another example. This looks like log 10 is 0.1, then this equals -1. Therefore, this delta G prime is larger than 0. This is called the endogenic reaction. Okay, this is how this one will be expressed in a biochemical reaction. That's what it is. Okay, now we're going to talk about it. Then we want to talk about ATP. Okay, so we remove these. We want to talk about the next one. Okay, we remove these, we keep there, and we want to talk the next concept, which is the energy currency. So we were talking so much about the energy. We haven't mentioned about what's the energy currency for. But you already know, it is ATP. So we want to review some of the section and talk in more detail about that. Energy currency is ATP. First question, what is ATP? Can you give me the full name? It's an easy question. Adenosine 5' triphosphate. That's a full name. Lots of people don't know about that, like the DNA. What is DNA? What's a full name? So, adenosine 5' triphosphate. Can we draw a structure? Okay, let's draw it. Okay. 5 carbon sugar right here. Okay. H, OH, OH, H, CH2, right here. Then go here, H. What is connected? Right here. Can you see it? Yes. That's N, that's N, that's N, that's N. This is NH2. And this is, when you connect it here, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So that 9 is connected to the carbon 1 right here. Okay? And you also, of course, going to have some couple bonds. Okay, now go here, what we have? A phosphate. Then go here. So where are the high energy? Right here. Right here. So this section, we will say AMP, adenosine monophosphates. When you go here, ADP, adenosine diphosphates. When you go here, is ATP, adenosine triphosphates. This is the ATP structure, what it looks like. So what we want to mention, why we need to keep this guy here. ATP can be hydrolyzed, become ADP, and release phosphates. This is a reaction, is exogonic reaction. For itself. Why? Because people already calculate the delta G prime equals minus 30.5 kJ per mole. Which means ATP hydrolyzed become ADP and phosphates. It's about minus 30.5. This value, we took out this negative. If we write a positive, we call it phosphate transfer potential power. Okay? That is ATP goes to ADP and the phosphate equals that. And we know that in our biochemical reaction, there are some of the chemistry or some of the chemicals could do phosphate transfer and generate ATP. Why? Because their phosphate transfer potential power is more than 30.5. So I gave you some of the examples. 1,3-biphosphoglycerate. What is 1,3-biphosphoglycerate? COOP. CHOH. CH2OP. That is 1,3-biphosphoglycerate. What is phosphor transfer potential power? It is about 61. Yes, it is about 62. 61.9. Another chemical right here. Sorry, this guy is 45, about 45. Another chemical, phosphoenolpyruvate. What is phosphoenolpyruvate looks like? This is phosphoenolpyruvate. The potential phosphor transfer power is 61.9. These two chemicals, the power is more than 30.5. Therefore, these chemicals, the phosphate, could be donated to ADP and then become ATP. This is a concept for substrate level phosphorylation. But at the same time, you could be asking, there is some other chemicals which seems or really looks like it has a phosphate transfer power. For example, glucose 6-phosphates. Is that right? Glucose 6-phosphates. cannot do phosphor transfer, cannot generate ATP? Because for this guy, the phosphate potential transfer energy power is only like 13. This is less than the ATP hydrolyze itself. Therefore, this chemical cannot do the phosphate transfer by itself. That's why we call this chemical is a low phosphate transferring chemicals. Okay? These are high phosphate transferring chemicals. So that's a reason to explain substrate level phosphorylation. And where they come from, it comes from this delta G value. And delta G value comes from here. And where is this delta G originally comes from? Comes from Gibbs free energy equation. So that's why we have to explain to you this story. And this table here will explain to you what I wrote there. So if we read through this, ATP said to have a high phosphate transfer potential. It readily sends a phosphate group to other molecules and expressed as a hydrolyzed removal of phosphate delta G value. And if you took out of that, negative will become a phosphate transferring potential. And then you could be seeing phosphoenolpyruvate, 1,3-biphosphoglycerate, their phosphor transfer potential value is higher than the ATP itself. But glucose 6-phosphate and glucose 1 glycerol 1-phosphate is much less than that. And if you don't know what I'm talking about here, then you need to go back to review glycolysis. We will talk real quick. Glucose becomes 1,6-biphospho-glucose. And finally, it becomes a pyruvate. And somehow right here is 1,3-biphosphoglycerate. Somehow before pyruvate, we say right before pyruvate is phosphoenolpyruvate. Those are the two places which is created ATP during glycolysis. And those phenomena we call it a substrate level phosphorylation. And this is a whole story. We talk about substrate level phosphorylation. So if I want to say, give a termination or give a definition for phosphorate, the substrate level phosphorylation actually is complicated. And lots of you will say the ATP generates without electron transport chain. Lots of you will answer like that. Oh, that's okay. But I gave you a joke. It's the same thing like I asked you why he's a boy because you said he's not a girl. Okay? So, but this is the whole story when we talk about it. At the end of the day, we need to go back to see the phosphotransfer potential power. Okay, so we get down from here. So when you study, how are you going to study? First law of thermodynamics is easy. Second law of thermodynamics is a little bit difficult. So this is ATP structure is easy. This one, it's all the conclusion of the slides. But I tell you, if you really have to understand, if you need to understand what I wrote there for the 3 example, a ball coming down, a dissolved closed vessel, and a cherry bomb. That can explain this equation very well. And then you go here, this is a standard equation, a biochemical reaction for pH at 7. So basically it's called about neutralize. If the pH at 3 and 4 is different. And this is basically is mass. And this talk about the definition of what is called the substrate level phosphorylation. So these type of the work, you have to combine these 5, 6 slides all together. Then you can understand. You cannot just remember them each single slides by single slides. Okay? Next question. Oxygen reduction reaction. This is another big topic we want to talk. And then we will move on to electron transport chain. We mentioned several times briefly. We want to talk a little bit of detail right here. So we take all these out. We go to next topic. Oxidize reduction reaction. Okay, the first thing, redox reactions. Oxidation, reduction, reaction. We say redox reaction. Yeah, I don't like these acronyms. It's not confusing people. First of all, you need to know what means oxidation. What means reduction? This is going to be using electron transfer as a concept. What is oxidation? Lose electron. What is reduction? Gain electron. Lots of you confusing. Okay, the easiest way to do. Do you know an exam test called the GRE? If you go to graduate school, you probably don't know some people because it's waived right now after pandemic. Graduate recording exam. But here you can see gain electron reduction, or we say reducing reduction. Is that right? That's a GRE. If you remember this exam test for go to graduate school, then it's easier to understand. Okay, if you still don't understand, what are we going to say? Reduction, think about an apple, a very juicy apple. It's reduction. Or 18 years older young girl's face. It's a reduction, lots of energy there. Okay, how about oxidation? A dried pear, a dried apple. You don't like it. And said very rudely, 80 years old grandma's face. That's called oxidation. So that's just some example, some joke to let you understand it. But you always remember, these two are also coupled. Reducing and oxidation, the electron transfer has to be circulated in the life. If they are not recycled, which means electron has to be recycled. You always remember, if this guy is not recycled, then the bacteria will be dying. Okay? Once you reduction, what do you have? You get the electron. That electron is become a potential energy, going to use to some of the work. You cannot accumulate there. But when you oxidation, you lose electron, you have to get more electron to recover. And finally, if you cannot control, which means your oxidizing is much more than reducing, for bacteria, that means they are going to die. It's easy to understand. Okay, next one. We go back to a very easy chemical question. CND. Okay, here's the example. A is, somebody will say this is nonsense. A is losing electron. How about that? Okay, lost electron goes here. Can you tell me what is reduced product? What is oxidized product? It's a very easy review of chemicals. What is reducing agent? What is oxidizing agent? Well, let's look at this. A losing electron becomes C. So what is C? Oxidized products, is that right? If C is oxidize the products, which one is reduce the products? That's B. Then what is A? That's a reducing agent. Then what is B? The left is B, oxidizing agent. Okay, so that's a very simple chemical concept. So you should know about these. We will mention one example later on when we talk about fermentation. Okay, next couple of slides, we want to talk about electron transport chain and relate to chemosmosis, and we talk about all these slides. Okay, next one, electron transport chain. Acronym ETS, or ETC, sorry, simple. So what is electron transport chain? And I draw a couple of times already, so we want to talk about that. That is basically a standard is NAD, H2, so FAD, and then go FMN, FES right here, then coenzyme Q, then go cytochrome C, then you go cytochrome A3, then you go cytochrome A, and finally is oxygen. Okay, so the electron is transferred like this. So we draw the electron transport chain right here. Then we want to talk about what are they? Those here. So first question is very simple. Number one, where is electron transport chain? In bacteria or prokaryotes, it is at cell membrane system. Okay, that's very simple. How about for fungi? Yeast and molds. In other words, it is eukaryotes. Where it is? Mitochondria. Mitochondria. That's the location of the electron transport chain. Okay. Second, the ETC components. What are those? It's not about chemical reaction, about chemistry class, so we talk a little bit briefly. What's the full name of NAD? Nicotinamide adenine dinucleotides. What is FAD? Fulvene adenine dinucleotides. What is FMN? Fulvene mononucleotides. What is FES? Iron sulfide. What is COQ? Coenzyme Q. What is cytochrome C? Cytochrome AA3. It's like a hemming with iron. Is that right? These three is iron and hemming. Finally is oxygen. Okay, so that's easy. We just go briefly. We don't talk that too much. Number 3, order. This will be a big question. So why the order like that? How come NADH to FAD is always on the top, the oxygen is always at the bottom? This comes with a good slide is right here. This tells you what it looks like, okay? So here we want to talk about electron is always from electron donor to acceptor. So if you have a donor, you transfer electron, go to acceptor, add electron. Now, how do we know it is a chemical, is a good electron donor? How do we know it is a good acceptor? We have a very important test called two-half reaction. Why we say two-half reaction? Obviously, it's called a redox reaction. Half of them is oxidation, half of them is reduction. So we call it a two-half reaction. The two-half reaction could be using delta E 0 prime to express it. What is delta E 0 prime to express it? This is originally coming from a formula which is minus NF delta G 0 prime. It's also a physics formula. N is a fixed mole unit. F Faraday constant. It is approximately somehow like 19 cal per mole. What is delta G? Where they comes from? Gibbs free energy equation. That's why we want to talk, because this delta G, delta E from two-half reaction right on the slides, which is also come from the free energy equation. Okay, let's give some of the examples. If NADH becomes NADH2, what's the delta G value? Or what's the delta E value? Minus 0.42 around. So that's the top one. How about the bottom one? If this bottom one happens, at the end of the day it's become water. What's the delta E value? Positive 0.81. So this tells you, based on the two-half reaction, the delta E expressed as a voltage, it gave you the conclusion is more negative, more potential, and electron donor